So are low speed, small scale air and water boundary layers really thin? So we're going to consider a flow that's moving at 1 foot a second past a 1 foot long plate, and I want to know what the trailing edge boundary layer thicknesses for air and water would be. So a little bit more terminology. Leading edge would be the front end, trailing edge would be the back edge. So what we have is I've got a 1 foot long plate, and this is capital U. What is that telling us? That's telling us the free stream velocity is 1 foot per second. So we want to know the trailing edge boundary layer thicknesses for both air and water at 68 degrees. So what do we have to do? Well, we have to look up kinematic viscosity because we're going to calculate out Reynolds number. So kinematic viscosity of air at 68 degrees is 1.61 e to the negative 4 foot squared per second. And then we can look up water, and water at that same temperature would only be 108 times 10 to the negative 5 foot squared per second. And so from here, what we need to do is we need to calculate out the Reynolds number for each of these, and then we can use that Prandtl-Blasius approximation that I had given you in the last lecture and calculate out what? Ooh, there's not a slide there. There we go. Now there is a slide there. So let's calculate out Reynolds. Let's not do this in red. Reynolds number based on length, and we're going to do the air first. So that's going to be velocity. In this case, it's our free stream velocity times our length, because we need to know the Reynolds number at the location that we're trying to calculate this, divided by kinematic viscosity. So 1 foot per second times 1 foot divided by 1.61 times 10 to the negative 4 foot squared per second, yes. Foot squared on top, second, foot squared over second on bottom, cancels out, unitless parameter, that's good. That Reynolds number is going to be 6,200. So this is laminar flow. So we go to our approximation, the boundary layer thickness over the location of the boundary layer, 5.0 times Reynolds number based on x to the 1/2. And so that's going to equal, our x is 1 foot, multiplying through, and then get 5.0 divided by 6,200 to the 1/2. And we calculate that out, and it's going to be 0.634 feet, which is about 3/4 of an inch of water. Excuse me, of air. So that's 1 foot, 3/4 of an inch. That's kind of small. That's not super small, but that's pretty small. Let's take a look at doing this for water now. So Reynolds number based on length is the same thing, UL over nu. So 1 foot per second times 1 foot divided by our kinematic viscosity of water, 1.08 e to the negative 5 foot squared per second. We bash that together. That's 92,600. So now that definitely gets us into territory that's still laminar flow. Because remember, we need 10 to the 6 to get turbulent. And so delta over x is still just going to be 5.0, Reynolds number based on x to the 1/2. So 1 foot times 5.0 divided by 92,600. And we'll take the square root of that. We bash all those together, and we get 0.0164 feet, which is about 2/10 of an inch. Nope, not foot, inch. So, yeah, the boundary layers compared to the height for these two materials at that temperature are relatively small.